Hi everyone, my name is Shiva. My topic is modulation compression in next generation. There is air interface and frontal trade-offs. 5G networks are anticipated to enable diverse applications with various requirements on data rates and latency. To meet the requirements, 5G new radio NR, that is, access technology includes key enhancements such as wide channel bandwidth operation, aggregation of multiple carriers, large multi antenna systems, multi stream transmissions, high modulation orders, and flexible frame structure with reduced transmission time intervals. The 5G NR enhancements increase the amount of data that can be transmitted per transmission time interval and also reduce the processing times for the bulk of data in 5G networks. This poses significant challenges for the radio access network RAN architecture. The enhancements are expected to become more demanding in beyond 5G networks, and the challenges are also expected to be further accentuated. Indeed, due to the trend of reduction in average revenue per user, the revenue of mobile network operators MNOs is not expected to grow. Next, NR RAN architecture and functional splits. This section reviews the logical architecture and the different functional split options that have been studied in 3GPP for 5G NR and the recent work in ORAN. Then we use analyze the requirements that the different splits between BB entities impose on the transport and network. 3GPP, the logical architecture of a GNB in 3GPP consists of a CU and one or more DUs that are connected with the CU as specified in TS 38.401 and shown in figure 1 left side. The F1 interface is defined to provide means for interconnecting a CU and a DU of a GNB. Two F1C and F1U provide control plane and user plane connectivity over the F1 interface as specified in TS 38.470. Each DU connects through a frontal interface to one or more RUs, which basically include the RF part but not BB processing. CU and DU are both logical nodes, including different G and B functions, depending on the functional split option. As part of an NR release 14 study item, which resulted in TR 38.801. 3GPP studied different CUDU functional splits. More precisely, 8 possible functional split options were proposed, as summarized in Figure 2. Option 8 is the option used for traditional CRAN in LTE and for which the Common Public Radio Interface CPRI was used as a baseline protocol. Reuse LTE dual connectivity DC has baseline protocol. Option 1, 4, 6, and 7 are also enabled in real networks thanks to eCPRI, an enhancement to run CPRI over switched Ethernet. Basically, proceeding from option 1 to option 8, the user plane capacity requirement of the transport interface progressively increases and the latency requirements becomes more stringent. However, extending the splits towards lower layers retains coordination gains in terms of multi-cell signal processing at the CU. After the analysis of the different functional splits in the study item TR 38.801, 3GPP has agreed in TS 38.40 that the GNB logical architecture focuses on option 2. PDCP, this RLC split, thus option 2 was adopted as a basic for normative specification work in release 15. Although other split options remain under consideration for future releases. In spite of the agreement, the design of intra PHY split option 7 has received significant attention in 3GPP, and a study item was conducted in release 15 to analyze CUDU low layers splits for NR, leading to TR 38.816. Different subvariants of option 7 were proposed for the downlink DL and the uplink, namely 71, 72, and 73, depending on the PHY functions that reside in the CU and the DU. In brief, the IQ overhead for option 73 scales in terms of coded bits. Option 72 scales with the number of spatial layers of IQ samples, and option 71 scales with the number of antenna elements. Option 2 is taken as baseline in the 3GPP release 16 by 17 work items. Aside from that, studies on CUDU splits, next generation RAN architectures and infrastructures have not continued in 3GPP release 16. However, a new Alliance ORAN has been created. In traditional CRAN for 4G LTE networks, the CPRI protocol was used as the transport protocol over the frontal to encapsulate DL and UL IQ samples. However, the use of CPRI applied to 5G NR exposes several limitations, such as the handling of multi gigabyte per second user plane traffic and point to multi-point CUDU DURU connections. To address such limitations, the eCPRI transport protocol has been developed recently. eCPRI enables efficient and flexible radio data transmission via a pocket-based frontal transport network like IP or Ethernet by providing various user plane data specific services. Different from CPRI, eCPRI supports more flexibility in the choice of the intra PHY functional split. In particular, the specification defines 5 of functional splits A, B, C, D, E, and 3 additional intra PHY splits. 2 splits for DL, ID, and IID, and 1 split for UL, UL and IU. In line with those analyzed by 3GPP. Even so, the wider carriers bandwidths use the use of massive multiple input, multiple output MIMO. Higher modulation orders a large number of aggregated carriers, and higher frequency ranges of NR require enhanced compression schemes to limit the frontal capacity requirement. In particular, under functional split option 7. Next, end-to-end simulation analysis. For the performance assessment, we use the NR modulation of NS3 with the new NR based PHY abstraction models developed in, and the 3GPP spatial channel model developed in, which is complement with the TR 38.1901 and valid for 0.5 to 100 gigahertz frequency bands. Scenario, we use a typical hexagonal site development. Each site has 3 cells with 3 uniform planar antenna arrays that cover 120 in azimuth each. We deploy a central site plus 6 additional sites belonging to the first outer ring, leading to a total of 21 cells, 21 RUs. The deployment assumes a frequency reuse of 3. Each cell of a site transmits in a separate frequency subband so that antenna arrays of the same side do not interfere. We use the 3GPP and urban micro scenario characterized by an intersite. Next, modulation compression. 7 and is a lossless compression technique that operates over DL user plane modulated data symbols before being transmitted over a frontal interface. This transmission involves encoding such IQ symbols into a number of bits W. Henceforth, bit width in this context, modulation compression aims at reducing the bandwidth to code a given modulation constellation point. Note that if no modulation compression is used, the bit width is usually fixed at W equals to 32 bits for both I and Q samples, regardless of the modulation order used. By means of modulation compression, however, the bit width can be adjusted according to a maximum modulation order that is used over the air interface, thus allowing a reduction in the capacity requirement over the frontal. To do so, a shift in the supported modulation constellation points is required in order to overlap and match the IQ symbols across all the supported modulations. In this way, a single encoded constellation point of size W can represent multiple IQ symbols belonging to different modulations. In particular, the bit width W can be chosen corresponding to the modulation order needed to represent the largest constellation in the data block. In particular, the bit width W can be chosen corresponding to the modulation order needed to represent the largest constellation in a data block. For example, if a data block to be compressed includes both um, 64 quadrature amplitude modulated, that is QAM, and quadrature phase shift keying, that is QPSK, symbols corresponding to multiplexed data and control channels, a bit width of W equals to 6 bits could be required. The constellation shift is illustrated in figure 3 for the modulations considered in NR. Figure 3 also illustrates how a signal bit width can represent IQ values of multiple constellation sizes. Example, see set dots for QPSK over the different shifted constellations. When decompressing, the RU must unshift the constellation and also apply a scale factor for the constellation types represented in the block. With modulation compression, frontal capacity reduction is achieved by using W equals to M bits for IQ bit width, where M is the modulation order instead of the typical W equals to 32 bits over option 7 to 2x in table 1. As an example, assume 20 MHz bandwidth, 0.04 PRB overhead. Numerology 1, 30 kHz subcarrier spacing, that is 14 symbols per slot of 0.5 ms, and one layer in NR, the required frontal capacity for 1U. Conclusion. In this article, we have reviewed the architectures, functional splits, and the frontal compression techniques for 5G NR defined in 3GPP and ORAN. Then, for a promising frontal compression technique, modulation compression, considered by ORAN, we have studied how modulation compression impacts the air interface performance, and we have analyzed the uh, related frontal capacity requirement in an end-to-end dynamic multi-cell simulation built with NS3 NR in an urban micro scenario with 21 cells. We have observed that for all traffic loads, reducing the modulation order down to 64 QAM has a negligible air interface uh, degradation and can, in some cases, slightly reduce end-to-end delay. A higher modulation order reduction does not show performance degradation until 16 QAM for medium loads and QPSK for low loads. Thus, modulation compression is proven not only to be effective technique to reduce the required capacity of the frontal interface, reaching a 75 to 94% reduction, but also to enable negligible degradation of the radio access interface. Thank you.